All right, hello, my name is Alina Logani. I'm going to walk us through an optimization problem today. It is problem number 41 in section 14.7. And so what we'll be doing is we're going to be using the second derivative test in order to find the minimum distance from a certain point to a plane. So our certain point is 2, 0, -3. So I'm going to zoom in here. We want to minimize the distance between this point, 2, 0, -3, to the plane x plus y plus z equals 1. We should be thinking of a few things here. The first is that this plane equation right here is the constraint of our problem. So what we're trying to do is we're minimizing a certain function given the constraint of the plane x plus y plus z equals 1. So what that tells us is we need an equation that we can minimize in order to get to to the optimization that's asked for. Well, that equation is the distance formula. Remember that the distance formula from a random point x, y, z to 2, 0, -3 is this. You do x minus x1 or 2, y minus y1 or y minus 0, which is y squared, and then z minus z1, which is z minus -3 squared or z plus 3 squared. And what this does is this gives us the equation that we want to minimize given the constraint of the plane x plus y plus z equals 1. So we can get started now. This is just restating we want to find a point on the plane x plus y plus z equals 1. So what this is telling us is we have a random point in this distance formula, x, y, z. And we want to make sure that that point is on the plane so that we can indeed minimize the distance from our point 2, 0, -3 to that point, which is on the plane. So in order to do that, we need to solve for one variable. And this time I've picked variable z in which to solve for. And you want to plug that into your distance formula. So what we did here, we have our plane, right? X plus y plus z equals 1. What I did was I solved for z. So with just some rearranging, you get z equals 1 minus x minus y. If you plug this into d, it will help us do two things. First, it'll help us minimize d, which we can only do when we're working with two variables. And it'll also help us put the point x, y, z on the plane P. So here I've rewritten the distance formula. Now what we want to do is we want to plug in our point for z. So what we have here is x minus 2 squared stays the same, and our y squared stays the same. But instead of z, we plug in what we solved for z. So you get plus 1 minus x minus y plus 3 squared. And you want to minimize this. Now, a trick that we learned in class is that instead of minimizing the actual square root, we can just minimize what's inside the square root. So instead of minimizing this whole thing, we just want to minimize whatever's inside of it. So I've rewritten this here. So to minimize it, I kind of solved for the square root. D squared equals f of xy. And here we can just write whatever's in the inside of the square root, which is this. And I've just combined terms in this here to get 4 minus x minus y squared. Now, the first thing we need to do, now that we have our final equation of the distance formula that is only two variables, is we want to be able to find the critical points. The first thing to do to find critical points is you need to take the partial derivative with respect to x. So if your f of x, if your f of xy is this equation, your f of x, partial derivative with respect to x, will become 2 times x minus 2. And then you cancel out that y squared because it doesn't have an x in it. And then you do plus 2 times 4 minus x minus y times -1. And what you do to find a critical point is you set this equal to 0. So what that gives us is 2x minus 4. And then note that this is really just a -2. So we want to do -8 plus 2x plus 2y is equal to 0. And what we're going to do is we're going to combine like terms here. So you get 4x plus 2y is equal to 12. And you can simplify that to being 2x plus y is equal to 6. Now here, I'm going to just quickly minimize this. Literally minimize, not mathematically. And we want to find now the partial with respect to y. And that's going to look very similar to what we did above. I'm just going to quickly solve it. This is your partial derivative with respect to y. And again, you set this equal to 0. So that gives you 2y. And again, this is a negative 2. So you want to do minus 8 plus 2x plus 2y is equal to 0, which makes it equal to 4y plus 2x equals 8, which again, you can simplify to 2y plus x is equal to 4. Now, what I did here was I solved. The next thing you want to do is you want to actually solve for x and y. You want to find the numbers that make up the critical point. So what you want to do is rearrange to solve for one of these variables. So I decided to solve for this one right here. And it ended up being x equals 4 minus 2y. And you plug it into the actually the above equation over here. So what you do here is if you've got your x equals 4 minus 2y, you plug it in. So above, if you have 2x, it becomes 2 times 4 minus 2y plus y equals 6. And this is really just your x term found over here. And that ends up being, once you go through the math, which I can pause here for a second so you can look at it. But I already solved it through, and that is y equals 2/3. I did that to save time, but this is the mathematical steps here. And once you have your y, you can plug that into either one of the equations found here, either this or to this, and you will get y equals 2/3. So you plug it in. So I chose to plug it into the equation I solved, which was x equals 4 minus 2y. And you get x equals 4 minus 4/3 because 2 times 2/3, which ends up being x equals 8/3. What you want to do now is, here's your critical point. So now that you found your x and y, you have 8/3 and 2/3 as your critical point. Now what you want to do is you want to use the second derivative test. You want to use the second derivative test in order to figure out if this term is a max or a min or a saddle point. So what we do here, in order to do a second derivative test, you actually have to find the second partial derivative with respect to each variable. So if we have, and I've rewritten it here, we found that the first partial derivative with respect to x is 4x plus 2y minus 12. Your second partial is just 4. And if you do the same thing with the partial derivative with respect to y, you get that the second partial is also just 4. And then if you do the partial of x and then the partial of y, you get 2. And that's the same for fxy and fyx. Your d equation, which I've written here, then becomes 4 times 4 minus 2 squared, which is equal to 16 minus 4, which is equal to 12. And what this tells you is because d is positive, you actually have a local min at 8/3 and at 2/3. Now that we know that this is a local min, we can solve for d. So what you want to do is you want to plug in both of these terms, 8/3 and 2/3, into your original distance equation that you had solved for two variables. So I've rewritten that up here. You want to plug in, like I've written, you want to plug in 8/3, 2/3. So with that, I've just sped up the math process here, so I'm going to pause it and let you guys see. But just plugging in 8/3 and 2/3, you end up getting this part right here, 2/3 squared plus 2/3 squared plus 2/3 squared. So in order to find d squared is clearly 4/9 plus 4/9 plus 4/9, which is equal to 12/9. So d is the square root of 12/9, which is just the same thing as saying 2√3/3. So this is the minimum distance, the shortest distance from the point 2, 0, -3 to the plane x plus y plus z equals 1. And remember, we had to do this because we find that the plane is a constraint, so we have to find a point on the constraint and then minimize the distance between this point, 2, 0, -3, to the point on the plane that is going to minimize our distance. And we find that the minimum distance is 2√3/3. We can actually find the point x, y, z that gives us that minimum distance. We've already found x and y, which is 8/3 and 2/3. We could just plug it back into here to find z. I'm not going to do that just because the problem doesn't ask for z, it just asks for the shortest distance. But yeah, here is our final answer. Thank you.